Okay, so I want to give you a short introduction to a space mission that we have put together, or we are trying to put together, and we have proposed to ESA in answer to the M7 call. Unfortunately, we have not been allowed to go forward because it was considered as too complicated, but I think it's still worth discussing that and getting ready for future opportunities. So it builds on this Voyage 2050 process, for which we submitted coordinated white papers, 4 coordinated white papers, 3 on science cases, which are complementary, and 1 which sort of argued that there could be a program, including an L-class space mission, to do all of this science. And this was quite well received by ESA. But you know, with a selection of spectral distortions as a potential L-class, and these other 2 science cases could be implemented within M-class space mission. This is a list of people who have been working on this Voyage 2050 process. So as I was saying, this 1 specific science case was selected as potential candidate for an L-class mission, while these 2 were mentioned as potential science teams for an M-class mission, and also the senior committee mentioned that they could possibly be implemented in 1 single mission, which is what we tried to do for this M7 call. And so this is the question: what part of this backlight and line intensity mapping Voyage 2050 white papers can be implemented in an M-class ESA mission? And I will go into some of the details of what was proposed exactly next. So this is the entire science program that was advocated in this Voyage 2050, with several science cases. Try to exploit CMB fluctuations at Z equals 1,000 or so to the best we can, and then new things, CMB spectral distortions, not completely new, but haven't been touched for more than 30 years, perhaps now. CMB interactions at high to low redshift to map structures with lensing and with SZ effect. And then direct observation of the microwave emission of structures with atoms, molecules, and dust, again in most of the Hubble volume. We have been warned by ESA that there is no Christmas tree space mission for an M-class, and so we should not plan on something which does everything. So nothing that does absolute measurements plus spectroscopy, deep horizon imaging, a very large cold telescope, etc. It obviously doesn't fit in an M-class budget, and probably not even L-class, to be perfectly honest. And so we have to cut through this program and select what we think can be done in an M-class mission, and also is most interesting scientifically in the end of the 2030s, which is the typical launch date for M7 and possibly also the next M-class space mission at ESA. So what we decided to do is drop completely CMB fluctuations, primordial CMB, because this will be addressed between now and 2040 by CMBS4 and Lightbird, and perhaps in the next decade by a probe class mission such as PICO in the US. And doing better than that would be completely out of the budget of an M-class mission. We also decided not to concentrate on CMB spectral distortions, for which there was an independent proposal to M7, which requires very specific and different type of measurements with absolute spectroscopy. And so the idea is to concentrate on CMB interactions at Z less than 10, but excluding CMB lensing, which requires CMB, very, very sensitive CMB polarization measurements, and also mapping at structures through atoms, molecules, and dust. We need to further descope that because it's still a very big science program. So what we decided to do is to do science with mapping the baryons in the cosmic web in the form of dust, hot gas, and atoms and molecules, which are traced by CIB emission and LISZT effect, and line intensity mapping of some of the atoms and molecules that can be found in the high redshift universe. We decided to concentrate on the largest scales only, to do it full sky, plus deep patches at an angular resolution of a few arc minutes. This is here approximately 2 arc minutes with a cosmological approximate, which means give or take a factor of 5 as a function of what can be actually achieved. Map the baryons with line intensity mapping in the Z of 2 to 6 redshift range, to measure P of K and Z at redshift out of range of large-scale structure mapping based on galaxy surveys, such as upcoming Euclid, LSST, SphereX, DESI. And map dust at submillimeter frequencies, which is best suited for high redshift observations and is very difficult to do from the ground, in particular on large scale. What we do not propose to do is to map dark matter and measure cluster masses using CMB lensing, as I mentioned, because this would require a space mission which we can't afford. We don't try either to resolve the CIB into sources or detect lines in hundreds or thousands of individual galaxies, or resolve galaxy clusters, because this is better done from the ground with instruments like CMB-S4 to some extent, CPET Prime, ALMA, Atlas, etc. And we don't want either to duplicate ground-based observations in atmospheric windows below 200 gigahertz, which are done by CMB-S4 and Pathfinders or S3 type experiments, nor do high-resolution spectroscopy. Doing all of that does not fit in an M-class mission, quite obviously. So we cut the redshift range at a redshift above 2. This is here below 2, for instance, mapped with Euclid. And to observe the larger scales, in particular, this is interesting because we can see directly the primordial modes, which are not yet processed by astrophysical process and go in the nonlinear regime. So the science we can do with that is probe inflation, of course, structural evolution, which means constrained matter and dark energy, gravitation, neutrinos, and see baryons in structures to understand astrophysical processes in structures, map SZ clusters and high redshift protoclusters, which can be detected through their infrared emission, map missing baryons, velocity fields, and do cosmology. So, of course, this uses the KSZ effect. So let me start with the line intensity mapping and try to explain the rationale for what we proposed and what we could try to propose at the next opportunity. Observing the CMB is observing one map of structures at one particular redshift, which is about 1000, 1100. If we could observe structures through some other tracers at other redshift, we get access to a 3-dimensional measurement of the primordial power spectrum. So it's like getting many CMB maps at many different redshifts. And there is one way to do that. And in fact, we identified the C2 line, which means the ionized carbon line at 1900 gigahertz, redshifted to this redshift range as a good tracer for measuring structures at redshifts which are difficult to probe with large-scale structure surveys which are based on detecting galaxies. And the reason for that is summarized in this plot, where we have here the total integrated emission for various lines. It's a prediction. For various lines, we have here the well-known CO line, various elements of the CO ladder, the C2 line, ionized carbon, and then some other lines here. And this is the mean line brightness temperature as a function of frequency. And the redshift for this line is coded with this color code here, going from 0 to 10. And so what we can see here is that there is one line which dominates very clearly over a broad range of frequencies, ranging from about 300 gigahertz to above a terahertz, 2 terahertz, which is the C2 line. And the nice thing is that there is all of this range here, which goes from redshift of about 2 to redshift of about 6, where it clearly dominates. At lower frequency, it's the CO which dominates, but also it's the CO at low redshift. You see, this is all blue, and we have many lines which have to be identified. In this frequency range, there is one single line that dominates. Everything which is foreground is much lower, and it also probes the interesting redshift range that we want to probe. And so the idea was to concentrate here between Z equals about 2 to Z equals about 6, and do spectroscopy measurements between 300 and 600 gigahertz. So how well do we want to do that? There are two questions. The first questions we want to ask is what angular resolution, what spectral resolution? And this is linked to the size of the structures that we want to probe. We have here, of course, so this is connected to the size of the telescope. We have here the angular resolution we get as a function of frequency for a 70 centimeter telescope, 1 meter telescope. It scales, of course, like the size of the mirror or the inverse in terms of angular resolution. We can see here 300 gigahertz. This is, let's see, 1, 2, yeah, 300, 400, 500 gigahertz. We get to this type of angular resolution 2.1 to 5 per minute with this type of telescopes. Now, if we look at this plot here, we have here as a function of redshift, the angular size of structures of 3 comoving megaparsec here and 1 comoving megaparsec, which are typically the size of galaxy clusters. This here shows the non-linear scale. Everything on smaller scale, as a function of redshift, is in the non-linear regime. This is the linear regime, so this is where we want to observe. And this is the angular resolution we get observing the C2 line. So it's now frequency translated in terms of redshift for an 85 centimeter telescope. And so this is what we decided that we need. Of course, it's always better to have a bigger telescope, a more capable space mission, but it costs also more money. And so we decided that this is about the right size for an M-class mission. Now there is the dimension of the volume element, the voxel, in comoving megaparsec as a function of frequency for, so this is across the sky. So this is the angular resolution, which depends on the size of the telescope, which shows that we go in the range from 2.5 minutes to of the order of 2.5 megaparsec to about 10 megaparsec. And this is what we get as a function of the spectral resolution, R equals 300, 500, 1000, which means nu over delta nu of this kind of this order. So this is typically the range that we want to probe. Going much better than that is not so interesting for line intensity mapping, because then we start to get peculiar velocity limits. Okay. Oops, sorry. So to do this mapping, just to summarize, what we need is a frequency range of the order of 300 to 600 gigahertz, spectroscopy with a spectral resolution of the order of 500 or better, angular resolution of the order of a few arc minutes. And then, because we are not completely sure what is the exact level of the C2, we are thinking that we would have both a wide field, so do a full sky survey. This is the thing that can be done only from space. And also concentrate on a smaller patch of sky, typically 1 to 10% sky fraction deeper, where we would be completely dominated by the signal. And so the idea is that on a large fraction of sky, we can do measurements without being completely signal dominated, just to get a good measurement of the spectrum, for which it's not necessary to be signal dominated. And then a fraction where we go deeper and actually detect things at high signal to noise ratio. And this requires a map depth of the order of 1, let's say in a deep patch, to 10 kilojansky per steradian per beam size pixel. And in terms of the instrument, the idea is to use one of these or a few of these spectrometers on chips. This is the European Decima 2.0 sketch, where we have here an antenna which is coupled to a filter bank. And this single pixel detects all of the radiation in 347 spectral channels here. So for this particular instrument, it went from 220 gigahertz, it goes from 220 gigahertz to 440, which shows that it extends over an octave in frequency. And the idea was to take this kind of design, shift it a bit up in frequency, and this is the kind of thing we can use for this space mission. This is here a picture of a prototype. So the spectrum we get in one single pixel on the sky could look something like that. So this is typically what we would see for R of 1000, and this is what we would see for R of the order of 500. And all of these things that we see here is not noise. In fact, this is the signal we're interested in. This is the fluctuation of the total emission of the C plus line as a function of frequency and hence as a function of redshift. And we have here 1 kilojansky per steradian, 10 kilojansky per steradian, which explains the sensitivity requirement we put. This is here the same thing for this signal in 1 gigahertz channels width. But so this is for one pixel, and we get measurements like that for all of the pixels, which means that you can look at it as many spectra as that, as there are pixels on the sky, or as many maps of structures as there are frequency channels in this measurement. So it means that with line intensity mapping, we will get about 350 maps of structures at different redshifts from 2 to 6. So we access the 3D information, contrarily to the CMB, which is only 2D, with close to 5 billion volume elements, 5 billion voxels, which can be compared to Planck, for which the CMB measures structures in about 5 million independent pixels. So we are just moving one big step forward in terms of mapping structures with this kind of measurement, if it can be done. This shows one of the foreground contaminants, which is the cosmic infrared background, the CIB. We now have the same signal here on top of the total CIB emissions. So the CIB dominates. 10 kilojansky per steradian is here at the bottom of this plot, but we can still see very clearly these lines. And also the CIB emission is very smooth. So the idea would be to simply subtract this very smooth background here to separate the C2 from the CIB. In terms of spectral measurement for one particular version of the instrument, we came up with this kind of signal-to-noise ratio here at various redshifts. Here Z equals 217, 252, all the way up to 5.33. We have the expected power spectrum of the signal here in a thick black. And on top of that, the noise with here a cut, which is due both to the beam and to the integration along the line of sight in the frequency band. And so we see that for most of these frequencies, we are essentially signal dominated, not by orders of magnitude, but signal dominated in a deep patch. And we have a signal to noise of the order of 1 or a few in the full scan, on the full scan. So that would be the objective. It means that we would get very clean measurements of all of these spectra at all of the redshifts that are probed with the experiment. Okay, So that was the line intensity mapping part, but also we were thinking of mapping the structures with SZ effect and CIB itself, in fact. And this here shows the typical spectrum we get for a galaxy cluster, with here the SZ effect, thermal SZ effect, and contamination or emission from, in fact, infrared galaxies in the galaxy cluster. So this is a far infrared component. On top of that, which is not represented here, there is the kinetic SZ effect. And in order to separate, and also there is an effect which is due to the temperature of the cluster, which shifts this thermal SZ signal because of the electron temperature corrections due to the electron temperature. And the idea is that to separate all of these emissions and trace in typical large-scale structure how much gas there is, what is the temperature of the gas, what's the velocity of the gas, and what's the dust emission, in addition to, of course, emission from lines, as I've shown before. We need to map this over a large range of frequencies, which goes from, say, below 100 gigahertz to, let's say, to maybe a few terahertz here to get all of these back. And so the idea was to do that with an experiment which complements what can be done from the ground at low frequency here below, let's say, 200 gigahertz, with both the spectrometer covering this range and an imager which would cover this range in a number of bands to map the dust emission. Why is this interesting? Because we know that dust emission from infrared galaxies, when it's shifted in frequency because of the redshift, the bump moves from here at Z equals 8 of the order of 1 millimeter, which means 300 gigahertz. And while at low redshift, at Z equals 0, our own galaxy and also nearby galaxies peak at wavelengths of about 100 micron, which means 3,000 gigahertz. And so the idea is to map all of that. And if we have enough channels, we can look at structures which are detected, whether they are detected at all frequencies, which would mean that, if they are detected at all frequencies with something which is compatible with that, it means it's low redshift things. But if they drop out when we observe at shorter wavelengths, at higher frequency, it means that it's high redshift structures. And so it should be possible to decompose the CIB into contributions from various redshifts, provided we have large enough maps so that we can look for templates which are decorrelated. And then if they are decorrelated, they have to come from different objects. And the only way for them to decorrelate is to be decomposed into various redshift ranges. So for the SZ effect, I already touched upon that. We have here a more complete plot, which shows the various effects we want to measure. So thermal SZ effect here in yellow, with a relativistic correction in green, and kinetic SZ effect, and here is the CMB. And so again, here, by covering this frequency range, we can distinguish, we can measure the spectra, and so get measurements of the temperature of clusters and distinguish between KSZ and TSZ, and also the dust contamination clusters. So this is showing the frequencies to observe that. We have here atmospheric windows where we'll get data from CMBS4, from Silence Observatory. We also, and here atmospheric windows at higher frequency, which are a bit more challenging, but where it can be possible to do measurements on smaller fraction of sky, or with, let's say, more limited signal to noise ratio, or worse noise properties, let's say, but still two windows which can be used to observe. from the ground. And then we complement that with a spectrometer here and an imager going all the way up to 3 terahertz. Why a space mission? Well, essentially because of that. This is, of course, all of you are familiar with that. This is the atmosphere transmission at the ALMA site for various levels of precipitable water vapor. And so we see these atmospheric windows at the various frequencies here. There are atmospheric windows here, even at higher frequency, but only a very limited fraction of time. To do spectroscopy, because of all of these lines and because of the sensitivity that is required, it's interesting to go to space. For imaging, if we want to go all the way up to 3 terahertz, obviously we need also a space mission. The last point I want to make is after Planck and Herschel, there is not much here in the ESA program. Spica was cancelled. So Lightbird is ongoing. It's not an ESA mission yet, but there was a proposal, so we'll see what happens with that. But it's very focused on primary CMB, and for all of the science I've been describing here, there is not much in the ESA program so far, and perhaps we can try to argue and do something. So the last point I wanted to make is that we have a bonus science case, because we get this imager which maps dust all the way to 3 terahertz. And it's not much more complicated to do polarized measurements for these channels than to do simple intensity measurements, because polarized detectors have been developed, in particular for Spica Bebop instrument for this space mission. And so they are already at a reasonable level of TRL. There are also detectors based on kids, which have been used in the US, in North America. And the idea is to look at galactic magnetism with these channels. And so in the end, we put together a proposal with these 3 key science goals: cosmological model and fundamental physics, using the line intensity mapping to map the 3D distribution of structures in this redshift range, then map baryons in the cosmic web and trace structure evolution with both dust and hot gas, and then galactic magnetism and galactic dust emission with polarized observation of the dust emission in our own galaxy and in nearby galaxies. This is summarized with this table, which includes the spectroscopic measurements here to do the line intensity mapping, and then imaging observations to do both mapping the baryons in the clusters, in the cosmic web, and do the galactic magnetism science. So unfortunately, or sadly, this has not been allowed to move forward, mostly because of the complexity, the perceived complexity of the cooling chain. One thing I didn't say, I didn't want to go into the detail of the design, because anyway, this space mission has been turned down for the moment, so we have to rethink. But one of the key elements of that is that we need a cold focal plane at 100 milli-K or so, and also a cold telescope for the sensitivity. It doesn't have to be very cold. It could be of the order of 20K, 15K of the order, but there is much to be gained by having it actively cooled at lower temperature than can be achieved with passive cooling. Passive cooling is perhaps enough for the line intensity mapping case, although we lose a factor of 2-3 in sensitivity. But to do the observations in the terahertz range, there is much to be gained to be called. So also to some extent, ESA criticized us on the TRL of the spectrometers on chip, in terms of developing a demonstration plan for space qualification. So we need to further develop the cooling chain technology and to consolidate the thermal design, building on the space missions such as Athena. There will be progress continuing in the next few years. We have to build on that. In terms of detectors, spectrometers on chip are now installed in Chile and in the South Pole, I think. They will also be flown on a NASA-funded stratospheric balloon, Explain, the PI is Eric Switzer. What we need to do also is to consolidate the science case and the requirements with simulations, try to see if we can give up a bit on sensitivity and the requirements to make the mission more M-class compatible and resubmit in next opportunities. Perhaps also what we would have to do for one single M-class mission is concentrate on one type of measurements, either polarized imaging or spectroscopy. And this is something which we could discuss. So I anticipate that while we are not putting together a proposal now for phase 2 of the current ESA process, we will continue working to get ready for future opportunities. And if people want to join this effort, we plan to submit perhaps a few papers which study various aspects of this. And if people want to join, you are very welcome.